Okay, let's take a look at example Unit C2, page 6. This is an airplane flying 100 miles per hour at an elevation which is altitude of 10,000 feet in a standard atmosphere. That means we assume that the US standard atmospheric condition of 10,000 feet altitude. Let's determine the pressure at point 1, which is far ahead of the airplane. Okay. The pressure at the stagnation point on the nose of the airplane, point 2. And the pressure difference, if this airplane is equipped with pitot-static probe, pressure difference indicated or sensed by this probe, which is attached to the fuselage. Okay. So I'm going to, once again, let me just emphasize the real situation. This is a real airplane, which is in this case moving. Okay, moving with velocity, let's say velocity v0. This is the motion of this airplane, which is 100 miles per hour. Okay. Now we really need to think about equivalent situation at the wind tunnel. So you are going to place the airplane inside of the wind tunnel. Obviously the airplane is not moving at all, but because you turn on the fan, this is going to create (100 miles per hour) test section airspeed. This is V infinity, free stream. So these are equivalent. It's not necessarily exactly the same thing, it's only an equivalent condition. Okay. So question is, first of all, I'm going to define a particular streamline. Then along this streamline, you're going to set up two locations. Location 1, which is location of incoming free stream. Location 2 here, stagnation point. Okay. So obviously V1, this is equal to V0. This is the motion of the vehicle in non-moving air, which is free stream, 100 miles per hour. Velocity V2 is obviously 0, stagnation point. Okay, so let's just take a look at the problem one at a time. So let's say, okay, what is the pressure at point 1 far ahead of this airplane? Obviously, this is atmospheric pressure because it's not disturbed yet. It hasn't disturbed yet by this presence of airplane. Okay, so this is purely PATM at 10,000 feet standard atmosphere. Is that correct? Okay. So part A, to answer the question, the pressure at point 1 is PATM, standard, at 10,000 feet. So the answer is, you're going to take a look at the standard atmospheric property table, table C1 in Appendix C. This is a handout, so you can take a look at the handout. P1 you can get is 10.108 pounds per inch square psi. I just want to make sure the handout. So anyway, so I trust that you have a handout to look it up and then find out pressure at 10,000 feet. So this is standard pressure out of US standard atmospheric model. On the side, let's find out the density at this given 10,000 feet altitude. If you look up the same standard atmospheric table, you're going to get 1.756 times 10 to minus 3 slugs per cubic foot. This is the density standard value right here at this point. Since we are applying Bernoulli's equation, we assume that the density here, density there doesn't change. Okay? That's why I picked up the density here. We're going to use this density later. Part B. Okay. The pressure at the stagnation point on the nose of the airplane. Pressure at point 2. So now we are going to apply Bernoulli's equation between point 1 and point 2. Okay. So we are going to apply Bernoulli's equation between point 1 and point 2. We can say P1 plus 1/2 rho V1 square is equal to P2 plus 1/2 rho V2 square. Notice that gamma z term is already dropped because this is air. So we approximately take gamma air being 0. So gamma z1, gamma z2, both terms dropped off already. Another thing you know is velocity v2 is 0, stagnation point. Okay. And also v1 is 100 miles per hour. Let's convert this into feet per second by using multiply by 88 divided by 60. Then you're going to have 146.667 feet per second. That's velocity v1, v2 is of course 0. Therefore, from here, you can determine P2. P2 is P1 plus 1/2 rho V1 squared. We do know P1 is this value, 10.108 pounds per inch squared. Let's convert this to pounds per feet squared by multiply by 144. 12 inch for 1 foot square plus 1/2. Density we found 1.756 times 10 to minus 3 slugs per cubic foot times velocity square 146.667 feet per second. This thing is squared. This is going to get you pressure at P2. P2 is 1,474.44 pound per feet square. If you convert it to PSI by divided by 144. This is going to be 10.239 psi. Okay. One thing we have to be very careful about this is what kind of pressure are you talking about? This is absolute. Okay? Since we are using absolute here, you're going to get absolute value out. So this is PSIA, I should say. And this is also PSI. PSIA. By the way, atmospheric pressure is always absolute. We can actually alternatively say in terms of gauge pressure, which is actually kind of easier. What is the gauge value of this? Obviously, of course you know, this is a zero gauge. If you plug in zero gauge here, you can have gauge value of this one. The gauge value of this one is actually 0.131 psig. How do you get that? In other words, how do you convert absolute to gauge? You take the absolute value, subtract atmospheric pressure to get gauge pressure. So the answer for part A can equivalently be expressed by zero gauge, knowing that, hey, you know, pressure here is zero gauge, of course, local atmospheric. Sure? Then using that zero gauge value here, you can get pressure at the stagnation point is either 10.239 psi absolute, or you can say 0.131 psi gauge. So you can express answers both in absolute or gauge based. Okay? Interesting. So let's take a look at part C. Part C, the question is, what is the pressure difference indicated by pirostatic probe? As you may know, actually you should know, pirostatic probe senses only one thing. That is the pressure difference between total pressure and static pressure. This one. This is delta P. What is total pressure? Interesting question. If you think about Bernoulli's, once again, Bernoulli's equation is static pressure plus 1/2 rho B squared is equal to P T. This is essentially what the Bernoulli's equation says. So Pt minus Ps is 1/2 rho B squared. So this is how much pirostatic probe sense. This is actually essentially dynamic pressure. So another thing is, this total pressure is a pressure at stagnation point, which is this value. This is the total pressure. Total pressure, Pt, subtracted by static pressure. Static pressure is essentially, this is the static pressure. Okay? So this means 10.239 psi A minus 10.108 psia is going to get you delta P, which is dynamic pressure in psi, which is essentially that. 0.131 psi. So this is the pressure difference between total pressure and static pressure, which is essentially, this is the total pressure, this is the static pressure. If you take a difference between them, that is equal to the gauge pressure measured at the stagnation point, which is equal to dynamic pressure. Okay? So this is gauge pressure at the stagnation point, which is equal to the pressure difference sensed by pirostatic probe, which is essentially dynamic pressure, 1/2 rho v squared. Is gauge pressure at stagnation point. Okay? So there are lots of ways to look at this problem, lots of different expressions you can find. You can solve this problem based on either absolute pressure or gauge pressure. Okay? Then you really need to understand that pirostatic probe determines the pressure difference between total and static, which is essentially called dynamic pressure, which is equal to the gauge pressure at the stagnation point also. Okay? So let's familiarize yourself. Lots of different expressions of the pressures. Okay, it's very important in aerodynamics class later on. Now, I want to also discuss one more thing. This is actual situation. This is equivalent situation. When okay, so this is quite important. For the actual flight, pressure P1 here, this is 0 gauge. In other words, this is local atmospheric value, PATM. What about in wind tunnel, what is P1 here? Is this 0 gauge also? The answer is no. This is not the 0 gauge. This is minus 1/2 rho b square gauge. In other words, this is really low pressure, actually vacuum pressure. So this is how the wind tunnel operates. When you turn on the switch, it starts the fan. This fan induces the low pressure inside of the wind tunnel compared to the outside of the wind tunnel. Because of the pressure difference, inside of the wind tunnel being the low pressure, it is going to suck the air into. If you want to create a faster speed, you need to even lower the speed. So in other words, this velocity b square multiplied by 1/2 rho is going to be how much vacuum you need to create. Okay? Then the air is introduced in here. Then if you take a look at this streamline, this is the velocity 100 miles per hour. This velocity becomes 0. If the velocity becomes 0 right here, what is the P2? P2 now becomes 0 gauge. So at the stagnation point of the wind tunnel, pressure is local atmospheric. And right here at the free stream, pressure is really lower than the local atmospheric. So within a blow-down type of wind tunnel, the highest pressure you can achieve is, of course, local atmospheric pressure. Then everywhere else is vacuum pressure. Obviously that's true because there's no way you can compress air within the wind tunnel. So the highest pressure you can get is 0 gauge. Okay? So that's why the wind tunnel is not exactly the same thing, it's just equivalent. Okay? So airplane is tested under the much lower pressure environment. That's what the wind tunnel really is. Okay? So proper look at this problem is at the location 1, this is a 0 gauge. So location 2, at the stagnation point, this is really high pressure, higher than atmospheric. How much higher? This much higher. So that is the total pressure developed here. So if you move faster and faster and faster speed, this gets higher, higher, higher pressure. Wind tunnel test, which is opposite. Stagnation point is the highest pressure, which is local atmospheric. So if you turn this fan faster and faster and faster, what happens is pressure here is lower, 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 lower. Okay? So it's not the same thing. It's actually not exactly the same thing. So test condition-wise environment is a much, much lower pressure condition in wind tunnel. Okay? So let's be careful about those very, very fundamental difference between actual flight and wind tunnel test.